going to use a projectile problem to demonstrate how to use the quadratic equation, the quadratic formula. We've already seen how to solve quadratic equations by factoring or by completing the square. Well, sometimes you have to just resort to some ugly calculations with a calculator, and the quadratic formula can come in really handy for that. So we're looking at a situation where we're going to fire a bow and arrow off of a platform. Platform is 10 meters off the ground, or the launch point is 10 meters off the ground. We're going to fire this arrow at 30 degrees above horizontal, and we're going to fire it at 100 meters per second of linear velocity. So that said, if we're going to try to figure out when does this thing hit the ground. So the only other force acting on this, other than its initial launching force, we're going to disregard air, is gravity. So we have to employ the basic gravitational model. And in order to employ the gravitational model, we need to break the velocity up into its components of vertical velocity and horizontal, because for the gravitational, we're only interested in the vertical component. You may remember from your geometry that a 30, 60, 90 triangle has a relationship between the sides of a, 2a, and a root 3, where the component opposite the 30-degree angle is half of the hypotenuse. In this case, the hypotenuse is 100, so the vertical component of the velocity will be 50. And so it's a, 2a, and a root 3. The horizontal component will be 50 times root 3. If you want to use your trigonometric functions on your calculator, the sine opposite over the hypotenuse of 30 is 0.5. The cosine of 30 is going to be approximately equal to 0.87. So our two components of velocity, our vertical component and our horizontal component, are 50 meters per second, as if we'd fired this thing straight up at 50 meters per second. And our horizontal component is approximately 87 meters per second. But again, that's not going to come into play quite yet. We know that the vertical motion model is going to be equal to the height of the object after t seconds is going to be negative 1/2 times the acceleration due to gravity, which is 9.8 meters per second squared. So we got negative 4.9 times t squared plus the initial vertical velocity, t, plus the initial height. And I used I to represent the initial height. Some people use h sub 1 or s for starting. It's important that you not confuse this with I as an imaginary square root of negative 1 type thing. Anyway, so let's look at the rest of this problem. So if we want to find out when does this thing hit the ground again, we're asking when is its h equal to 0? When does this particular parabola, when does this h equal 0? And if we have our negative 4.9 t squared plus the initial velocity 50 times t plus 10, the initial height, we're asking when does this equal 0? We can employ the quadratic equation, quadratic formula, to this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we have x equals negative 50 plus or minus the square root of 50 squared, which is 2,500. Minus 4 times a negative 4.9 times a positive 10. This ends up being plus 196. So we have 2696 is our b squared minus 4ac value. And that has a square root of 51.9. So we end up with an answer of x equals negative 50 plus 51.9 over negative 9.8, or negative 50 minus 51.9 over negative 9.8. Now, you may notice right away that if negative 50 plus 51.9 is going to be a positive 1.9. And a positive 1.9 divided by a negative 9.8 is going to give us a value of negative something. And remember that actually x stands for t in this situation, because that's our independent value. we can't have a negative time. What does that mean? That means, well, the math doesn't understand that we're talking about a real situation. The answer that we get, the negative, is actually over here, prior to launching, but we're not interested in that. We're interested in the larger one, the one that's positive, the one after the launch. So we get this negative 50 minus 51.9. So we get, I'm going to do some quick calculations with my handheld calculator. We get approximately 10.4 seconds. So I would write t equals 10.4 seconds. So that is how long that arrow is in the air. Now, can we tell how far away it landed? Well, certainly we can, because if it was traveling in a horizontal component of 87, we can just take our time and multiply it by 87. And it was about 905 meters. That may be not exact because I didn't round on the calculator. So this distance here from the launch to where it hit the ground was about 905 meters. Okay? We can tell a lot of things based on the equation. We can actually tell what the highest point is. The axis of symmetry, you may recall. The axis of symmetry of a parabola is negative b over 2a is equal to x. So if we take negative b, negative 50 over 9.8, we realize that its highest point was 5.1 seconds after launch, okay? 5.1 seconds. Now we could take that t and plug it right in here. If we change this to h, we could take that 5.1, plug it in for t, and we could calculate exactly where that thing was, how high it was at its highest point. We could find out exactly when it was 25 meters above the ground, and it probably would have been, well, it definitely would have been 25 meters above the ground twice. We would do that by substituting in 25 for h and equaling this. Then we would subtract 25 from both sides to set it equal to 0, and again apply the quadratic formula. It's a very useful tool, but you need to be able to think about what it is you know, how to take it apart, and how to use it. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Very useful.